The capillary movement of the soil. This particularly comes into account when we have very sandy soil. Sands do not move capillarily sideways. And this becomes a major problem in drip. This isn't such a problem in areas where we're broadcasting the water over the surface. When we run true drip and we're putting water at a point source, it will not go laterally. It just goes straight down. So sometimes the intake rate could be very high, but you get no lateral movement of the water. And that can be a real bummer. Also, when we get into really, really heavy clay soils, we have to be aware that if we're putting it on too rapidly, it'll start to puddle up even on drip systems, because those clays, all the water's going laterally. It's not letting gravity pull it down very fast at all, so everything's going sideways. You end up with a big dish of water on a really heavy clay soil with drip. Big, round, thin plate of water. Whereas in sand, it's like a stovepipe, straight down. And then everything in between becomes more of an onion pattern off of a true emitter. Water vapor and evaporation. Again, as far as its effect on the intake rate, it will allow quicker drying of the surface, which will allow this continuum to shift back quicker when it's really hot out. So you can get back to your instantaneous rates at a high level when you have high evaporation and a lot of water vapor leaving the surface of the soil. And one way water does leave the soil is through water vapor, evaporating out from down in the heart of the soil itself and working its way up through the pores and evaporating out that way. So it leaves a path so that intake rates will increase where you have a lot of water vapor already gone out of the soil. Should help inspire the intake rates. And that's it on intake rates. Okay, this category now is water holding capacity. Every soil has a different ability to store water. And again, we can find the soil survey from a given area, from a given county in this country, and there, from that soil survey, you can find the soil type that you're working with, and that soil type, you can read up on that in the specifications. It will tell you the water holding capacity of that soil. For example, we have a soil like a Walla Walla silt loam that looks something like this. They'll say first foot. Say it held 0.20 inches per inch. Then if I had a full foot depth that I'm working with, I can find out how much water that soil held. And in this case, it would be 2.4 inches. Get my decimal point in the right place, of water in that foot of soil. So that's how much water could actually be stored. I got a foot's worth of soil, and if I just squeezed all the water out of that, I'd end up with about 2.4 inches of water drained out in it if I just drained it out into a cubic foot little column. So basically what it's saying is, I got myself a foot of soil here, and within that foot, it's going to hold, if I just squished all the water out, there'd be that much water in every foot. Now that it's displaced throughout it. But if I were to be able to drain all the water out of that foot of soil, I'd end up with that much water out of each foot. And it might be that way all the way down through the profile. If it's a soil that has a continuous profile of the same exact material, the second foot could be the exact same value, and the third foot would be the exact same value, and so on and so on, all the way through the profile. And that would tell me how much water was in that soil. To measure that, they can actually take the soil, take a volume of it, saturate it up to field capacity, and then just dry it out and weigh the differences between the two, and they know exactly how much volume of water was in it.